Hello students, and welcome to the video lecture on chemical reaction engineering. We were discussing on catalytic and catalysis reactor. Till now we have gone through various topics. This is something what we were covering in our video lectures for now. In the first video lecture we have seen a heterogeneous data analysis for reactor design, and we have seen multiple steps on how it is being done, taking from a crude experimental data and moving on to develop a rate law and finally getting into the reactor design after evaluating the different parameters. We then moved on to discuss on the different deactivation. So we discussed on sintering and aging, we have discussed on fouling and coking. We also discussed on the poisoning of the catalyst. We have seen the corresponding different rate forms, how the rate law for decay is being derived, and the activity plays an important role along with that of the concentration of species. We also solved a couple of problems on deactivation, and one specific to the sulfur poisoning and the crude FCC reaction. So today we move a step ahead on to see how this deactivation thing is being handled in a different reactor systems. So we will discuss on the reactor systems that will handle our decaying catalyst. So we start with our lecture number 4 there. So there are 3 different systems that handle this deactivation in a different way. When you have a very slow decay rate, that time we prefer to have temperature time trajectories. When we have a moderate decay, that time we have moving bed reactors. And when we have a very rapid decay, we go for STTR or straight through transport reactors. I will discuss in short 3 different videos, one being on TTT or temperature time trajectories. Next we'll discuss on moving bed reactors, and in the third video we'll try to address on straight through transport reactor. Moving on to the first one, the point to be noted that we are talking on slow decay. So we have multiple type of reactors that are employed in the petrochemical industry. At times this rate of deactivation which occurs by poisoning, the rate law is pretty slow. Now these are all continuous processes, and if your deactivation dominates, or rather it is continuing or going through the timeline, what will it impact is the throughput from your process. Now earlier, if I have 10 sites, that is giving me 10% conversion. Now as I move along, let's say after 3 days or 5 days, now my sites are only limited to 9 or 8. My overall throughput conversion will reduce to maybe 80. So this cannot be handled when it goes to the next step, and that is where the problem occurs. If you have a constant conversion necessity, your separation is the primary step which gets hampered if that alters. We don't have problem of having a reduction in activity in the reactor, but the subsequent steps which follow usually gets hampered. So our understanding of reaction kinetics says that if you can increase the temperature, the rate of reaction increases. Right? If the rate of reaction increases, your rate of decay is also increased. But if you compare the two rate, that is rate of reaction or the kinetics, to the kinetics of deactivation, it is clear that this rate is faster than the deactivation. So increasing the rate will give me higher value of conversion, while higher decay rate will give me reduction into the conversion. Now we are playing with temperature in such a way that we balance these two so that my throughput from the process or the conversion remains intact without hampering my any downstream processing. That is what it is being given in this paragraph. One way to maintain a constant conversion with the decaying catalyst in any of a packed bed or fluidized bed is to increase the rate of reaction by steadily increasing the feed temperature so that your conversion is not hampered and it returns to the constant value. So here we are considering a fluidized bed in the manner which is shown here into the reactor. So our aim is to develop a relation which will talk about two things: feed temperature of the reactor and the time. That is what we call temperature time trajectory. At what time, what temperature should be increased, or during what time, how the temperature has to move so that there is no change in the output of my reactor. And how we are going to do this is what we said here: increase the feed temperature in a manner that the reaction rate remains constant with time. So my initial rate is Ra dash at T0 and initial time. It is equal to the rate at any other moment of time with a different temperature than T0. Now this T is higher temperature than T0. Right? Now if you look at this rate, this is activity. Activity is actually contributing to the drop in the value of rate. This is the rate what it would have been at 0 time and higher temperature. Hope this is clear. This is rate at any instant of time and a higher temperature T. The actual rate at this temperature is reduced by this term, which is activity of a catalyst, which is okay. So for here now we are considering the first order reaction. So this side becomes K at T0 into Ca, and this becomes A of T into minus Ra is again K at temperature T into Ca. And we will neglect any of the variations in the concentration. This concentration terms we can neglect, so that we are now relating our activity and rate constant to the specific rate constant at T0. So that becomes K of T into A of T, that is equal to K0, which comes from here at 0 time and temperature T0. Our goal is to find temperature and time trajectory, how the temperature has to increase. So let us rewrite this. K in terms of T0 and T, you can write, we know from Arrhenius law, K0 exponential of E by R 1 by T0 is 1 by T. This is equal to K. If you remember it well, that becomes K1 by K2, that equals to K2 into exponential E by R 1 by T2 minus 1 by T1. Just that we are taking the base temperature as T0, we are getting this K of T equal to K0 from Arrhenius law. A we are writing as it is equal to K0. We are just trying to extract this 1 by T from here. K0 gets cut. This exponential gets transferred to A on the other side, and you will get 1 by T equal to R upon E ln of A 1 by T0. So this is also an Arrhenius type of dependence on the temperature. Now this was our first presumption for a first order rate law, where we are comparing our initial rate to the rate at any elevated temperature, both being equal. Let us write deactivation or decay law, that is minus dA by dt. Now this will be Kd. Now Kd is again Kd0 Ed by R 1 by T 1 minus T0. Kd A raised to power n. Now Kd0 is the reactivation constants at T0. This EA is activation energy for reaction. Ed is activation energy for deactivation or catalyst decay. Now you have found out this term, 1 by T R by EA ln 1 by ln A plus 1 by T 0. Now if you carefully look at the term 1 by R 1 by T0 minus 1 by T, what we are talking of, 1 upon T0 minus 1 by T into 1 by R, that becomes ln A upon EA. If you look at this term, this is what we have solved in here. So ln of 1 by A is EA by R 1 by T0 minus 1 by T. What we are trying to replace is 1 by R 1 upon T0 minus 1 by T. T0 minus T. This EA goes on the other side, so this becomes minus ln A upon EA. So this has been replaced in this equation from 115 into 116, and you get dA by dt is kd naught exponential minus ed by a ln A into a raised to power n. Exponential of ln gets cut, minus ed by a goes to the power of a plus a to the power n, so this becomes n minus ed by ea. That comes out to be here. So if you integrate this equation, activity being 1 or 0 and case where order is not equal to ed by ea, you come out to the form where you relate time to activity, activation energy, order. This is our purpose solved. We are looking for temperature to time trajectories. So we have time, but we don't have temperature in this, and we know that this can be then moved into so 114 for A and substituting in 118. If you look at here, your A becomes exponential of minus Ea by R, 1 by T0 minus 1 by, and that is being fed here, A being minus exponential of Ea by R, 1 by T minus 1 by T naught, which is being then solved. Now let us look at this expression. This is what we were looking for. This is time, rate of decay known, decay order known, activation energy is known, R known, initial temperature known. So putting all these things in place, you will be able to, for any rise in temperature, you will know the time at which it has to be increased, under what case, under the case where you want the rate and initial temperature to be the rate at elevated temperature for a first order reaction. I wish everybody to solve this at home calmly, composedly. You will be able to get the final form of equation. This equation is telling us how the temperature of a catalytic reactor should be changed or increased in order that the reaction rate remains constant. A very peculiar point we should be noting here that the decay rate law changes as the temperature increases, and that is where we are making a balance to see that those are being tracked well. For a first order decay, Krishna-Swamin control expression for temperature time trajectories is being given here, where if you look at what they are trying to do is KD0 into EA for first order decay. N is 1, so this becomes 0. N is 1, EA minus EA becomes 0. This is ED by R, so 1 minus exponential ED by R, 1 by T minus 1 by T naught, that is there, KD naught, and this becomes EA by EA upon KD naught into ED. So that's just a simple expression what we are having. One of an example is given here where temperature time trajectories for deactivating hydrocracking catalyst has been given here. If we look here, temperature keeps on increasing from 740 Fahrenheit to 820, so that the rate remains constant and the reactor can run up to like 250 hours. When working at a lower one, this is being increased so that the work can go up to 400 hours. So that's how it is. You can play with the EA, ED, KD, and these values are given to you. If you can put those values here and make the decay, you will be able to get the temperature time trajectory. So that is what we have for the day and the lecture. Keep exploring temperature time trajectories and solve this expression for yourself. So we understood the importance when there is a slow decay, how slight changes in the temperature can actually let our operation to go for a longer time and succeed on, and the succeeded conversion from deactivation can be then taken care. That's all for the day for the lecture. Thank you.